Welcome to Behavioral Consumer Analytics. Today we will continue our topic of decisions under uncertainty. And last time we talked about judgment under uncertainty and the judgment of probabilities. And today we will look into the evaluation of lotteries. So we will look at risk preferences, and in particular, we will take a look at prospect theory, which is basically a new version of a new model of risk preferences that has, to some extent, replaced expected utility theory in particular applications. And we will also, due to the similarity to prospect theory, talk about a theory of consumer choice, which is mental accounting. In the first part of this lecture, we will talk about risk preferences and prospect theory. And I put up a document for you to look at where you could get yourself into the topic already by answering some questions about lotteries and choices between lotteries. So there's a number of them, and it might be useful for you to do that, so that afterwards, when we talk about these decisions, you know how you reacted to them. Okay. So all of these we will see in just a second when we talk about prospect theory. So please pause the recording at this point, take a look at the document online, and tick your choices, and then you can continue here. All right. So once you've done that, let's move ahead and look into expected utility theory, where it might be just useful to see what is behind that theory. So we will spell out some tenets and axioms just to see what it is, and then we will basically look at some empirical evidence that has prompted the literature to move on and look at other models. So one of the tenets, basically the ingredients of the model that will not be questioned within the model, and there will be no particular mention of this construction as an assumption, is basically that utility is expected to be derived on the basis of an expectation. So here, the overall expected utility of a lottery that has outcomes X and probabilities P will be a term that basically combines the utilities of the outcomes with the probabilities of the event in a multiplicative fashion, and it's a sum of all these individual terms that then creates expected utility. So that is overall utility is expected utility. Furthermore, there's asset integration. So you basically accept a prospect if this expected utility from changing your wealth level according to the outcomes in different states of the world with a particular probability P, if this is evaluated to be greater than the utility of just having your current wealth status W. So the domain of the utility function is the final states, which is basically the level of final wealth that you have. So that includes your currently held own assets W. And then risk aversion is reflected with a utility function u, small u, that is concave, meaning that the second derivative is less than 0. All right, so these are some tenets, some things that go into expected utility without maybe necessarily being spelled out all too often. But furthermore, when there was a look into a particular expression of expected utility with a particular structure, then there were 4 axioms that von Neumann and Morgenstern used in order to show that if choices satisfy these axioms, then the preferences can be represented with expected utility. So here we have completeness, basically saying that you as a decision maker, you will always be able to state a preference, and that might be a preference for A, preference for B, or it might be both, which is taken as an indifference. There's the property or axiom of transitivity. So if for 3 lotteries A, B, and C, you prefer A to B and B to C, it must be that you also prefer A to C. That is just meaning that the agent decides consistently. There's the independence of irrelevant alternatives. So if you have 3 lotteries A, B, C, and you prefer A to B, and there's a number t between 0 and 1, then also adding with a certain probability 1 minus t, an alternative C to both A and to B should not change your preference, right? So if you then look at a gamble where with probability t you get either A or B, but also for sure in both cases you get 1 minus t times C, then you should still prefer the construction that involves A over the instruction that involves B. So 2 lotteries mixed in the same fashion with a third one should be treated just like the original lotteries. And then finally, there's a more technical axiom of continuity, which says that if you have 3 lotteries A, B, C, and you prefer A to B to C, then there is a probability P such that you can make the decision maker indifferent between B and the mixture between A and C. All right, if that is satisfied, then von Neumann and Morgenstern in the 1930s showed that the preferences can be reflected by a utility function such that preferences, for example, preferring A over B, will be equivalent to a number, a utility attached to A that is greater than the utility and the number attached to B. And then this theory allows for the discussion of risk aversion, where you have a small u function that is concave in wealth, or risk lovingness, where you have a small u function that is convex in wealth w. So you could have risk aversion, for example, with a function the square root of w. You have risk neutrality with a linear function, for example, u of w being w, and you have risk lovingness with a convex function, for example, w squared. All right, I assume that you are familiar and have heard of expected utility. So this is basically just a reminder. And if we think of this happening in the 1930s, we will take now another step into the 1950s, when the following paradox came out, which was due to a French economist called Maurice Allais, and this is called the Allais paradox, and it's as follows. So if you have a choice 1, as you did in your document, then you choose between a lottery A that yields with 0.33 probability 2,500, with probability 0.66 2,400, and 0 with probability 0.01. And the lottery B, the alternative, would yield 2,400 with certainty. And I'm highlighting in bold the decisions that are observed by the majority in experiments. So this is experimental work done by Kahneman and Tversky, and they observed that people predominantly prefer the certain lottery. And we can reflect this with expected utility, so we can translate the decision for B with this inequality. So the utility of 2,400 is greater than 0.33 times the utility of 2,500 plus 0.66 times the utility of 2,400. And then we assume that the utility of 0 be 0. And then you can rearrange this and you get an inequality. Now, if you look at choice 10, then you again have the decision between A and B. Now A yields 2,500 with probability 3.33, 0 with probability 0.67, and lottery B yields 2,400 with probability 0.34, 0 with the remaining probability. Here, the majority chooses A, and that would be reflected in an expected utility term of this sort. So 0.34 times the utility of 2,400 is less than 0.33 times the utility of 2,500. And what you can observe at this point is that here we derive exactly the opposite inequality from the one above. So that is the paradox of Maurice Allais, that you can make a choice 1, predominantly choosing B, and you make a choice 10, predominantly choosing A, which, if you express it in terms of expected utility, would actually lead to a contradiction, because you are free to hold whatever preference that you have. But if your preferences are looked at from the perspective of expected utility, then we get this contradiction, meaning that your preferences cannot be described by expected utility, because you should be stating one of the two inequalities. It shouldn't be both at the same time. So this was observed and published in the 1950s, and in particular, we will come to see that in more detail. This paradox derives from a violation of the axiom number 3, which is the independence of the irrelevant alternative. So basically, choices 1 and 10 are the same choices, just with different irrelevant alternatives that make an influence and have an influence on the choice that you make. All right, so this was one of the, if you will, motivations for prospect theory, which was then done and constructed by Kahneman and Tversky in the 1970s. And basically all the choices that you went through are taken from their paper from 1979 that introduced prospect theory. So they were able to explain a whole host of experimental results with their theory. So let's take a look at this theory. Prospect theory looks at regular prospects or lotteries. In this case, these are neither strictly positive nor strictly negative. But for the moment, the important thing is that we are evaluating this prospect by giving it a value that depends on the outcomes x and y and the probabilities p and q. And here the expression looks very similar to what we saw before. We have a function v that is a value function that is applied to the outcome x or the outcome y, and this value is multiplied with a term that depends on the probability p or q, and that is called pi, the weighting function of the probability, right? So where in expected utility we had this small u utility function that told us the utility of a certain wealth level, here we have a value function that depends on an outcome x and y, and instead of just using the plain probability, there is a weighting function that weights the probability. And so the key ingredients, therefore, are the value function and the weighting function. And let's take a look at these two in sequence. So the value function, I'm sure many of you have seen this or heard this before. The value function of prospect theory has basically three main characteristics. First, and probably most important, is that rather than defining a value as a function of the final wealth level, here we are looking at deviations from a reference point. Yeah? So we are looking at gains and losses, and in the middle there's a reference point. There's discussion as to what exactly that reference point is. It seems likely, according to the literature, that these are oftentimes the expectations that you hold as to what is your outcome, and then gains and losses are basically from this expectation, relative to that expectation, you would think about gains and losses. For example, you expect a raise of 1%, so this will be your reference point. You think there's a gain if you get a 2% raise, and you would feel there's a loss if you only get 0.5% of a raise. Okay, then if you look at these functions, you can see that the function is generally concave for gains, so you are risk averse in the gain domain, and it is convex for losses, so you are risk loving in the loss domain. So that are very different attitudes towards risk that are combined in one decision maker, if you will, depending on whether we are above or below this reference point. Also, you can see that the function is steeper for losses than for gains. So losses of a particular magnitude, they feel stronger negatively than gains of the same magnitude feel positively. So this is loss aversion, which is a very important ingredient in people's evaluation of risk, and that is here reflected with this very steep function in the loss domain compared to the gain domain. All right, so there's a lot happening in this value function. Let's take a look at the weighting function. Here we can see that the weight is increasing in P. That is what we would expect. The higher the probability, the higher is the weight that you attach to it. But it's not the exact 45-degree line where the weight is equal to P, which would be the dotted line. But we have this function that is basically above the 45-degree line for small probabilities and below this line for medium and high probabilities. Also, there's an assumption that at 0 the weight is 0, and at 1 the weight is 1. So there's, in a sense, the assumption that there's a jump from the weight being 0, but then it jumps up for small probabilities to a weight that is higher than the probability. And also for large probabilities, it is usually below 1 and well below P, but then at the probability 1, the weight jumps to be 1. There's overweighting for small probabilities, that's what I mentioned, and furthermore, there's subcertainty. So if you have a probability P between 0 and 1, then the weight of P and the weight of 1 minus P generally adds up to less than 1. So if you, for example, look at 0.5, if you have 2 times the weight of 0.5, this adds up maybe to 0.8. It does not add up to 1. All right. Maybe just as an aside, I'm always fascinated by the fact that small probabilities are said to be overweighted, but the probability of 0, the weight of 0 probability is actually 0. So there's this discontinuity, if you will. And if you think about these small probabilities events, there's also a question as to what is on your radar. What do you pay attention to if you, for example, think about insuring your car or your house? So which events do you consider as you think about this? And there might be some events that are small and you pay attention to them and then you overweight their probability. There might be some events that cannot occur and they will necessarily, be evaluated with a probability and a weight of 0. But there might actually be other events that could occur with a very small probability, but they are not in your mind, so you would still evaluate them with a probability of 0, right? Because you just don't have them on the radar. And I find it's a very interesting area of this weighting function. Anyway, let's continue and let's go back to some of the applications of this theory. We did see the Allais paradox, the common consequence, and with the help of prospect theory, we can to some extent explain what's going on in the decision maker and why do we observe the kind of choices that we observe. For example, in choice 1, it is relatively clear that the certainty aspect makes lottery very intriguing, very valuable because of this high weight that is attached to the probability of 1, right? When you then move to choice 10, there's no lottery that yields something with certainty, and you might think that the probability difference is so small that you go with the choice A because it yields a little bit more with basically the same probability. So this is how prospect theory might be able to explain the Allais paradox. So you basically have a sure gain in lottery B versus a probable gain in lottery A, and depending on how this is framed, you prefer either B or A. There are other, if you will, paradoxes that have been observed in the context of this Allais paradox. For example, there's a common ratio effect where if you get the choice such as choice 2 and you have a possibility of getting 4,000 with a probability 0.8 or getting 3,000 for sure, then people predominantly go for B. But if you have the same outcomes and the probabilities are just divided by 4, then you observe that the preferences reverse and you then prefer the 4,000, basically because the added benefit of this high probability weight from probability 1 does not kick in anymore, right? So at this point, the difference between 3,000 and 4,000 makes you prefer lottery A. And if you think about the weights attached to probability 0.2 and 0.25, they are even, though they are different, the distance between them in the weighting function is even below 0.05. It's smaller than the difference in the pure probabilities. So this is the common ratio effect that you might have seen yourself, exhibited yourself in choices 2 and 11. And then, well, choice 11 is choice 2, just in a compound fashion where you basically have choice 2 with probability 2.5 and you get 0 with probability 0.75. And reducing the winning probability from 1 to 0.25 has a greater effect than from 0.8 to 0.2. There's another way of having the same common ratio effect. In choice 3, you get a 1-week tour of England with certainty, but when in choice 12, you have the option, the choice between the two same options, but at a lower probability, then all of a sudden having a 3-week tour, including England, France, and Italy, trumps the 1-week tour of England, even though it has just half of the probability. I'm sorry, it's a 1/10 of the probability. Right, so choice 12 then is again choice 3 with probability 0.1 or nothing with probability 0.9. And so this is again the common ratio effect. And we did observe it again between choice 4, where we have the preference for lottery B, which yields 3,000 with a probability 0.9, compared to A that yields 6,000 with probability 0.4. And if you reduce these probabilities by quite a bit, then you see that people suddenly prefer 6,000 with a very small probability over 3,000 with an also small probability, but the probability is still double the probability for outcome 3,000 as in choice 4. So choice 4 has a substantial chance of winning in B, while choice 13 has a minuscule chance in both, but A has a larger gain. Okay, so there are more effects that we can observe. For example, if you look at choice 2 that we already covered, and then you bring these outcomes into the negative, into the loss domain, then suddenly you see a reversal of preferences. You don't want to have a sure loss. You would prefer to gamble and have only a probability of 0.8 of receiving this loss, even though the loss that you choose then would be a higher loss. And the same is true for the choices 11 and 14, where we again, we had the common ratio effect between choice 2 and 11, and now we see this reversal between choice 2 and 11, but there's also a reversal if we move from choice 5, which is in the negative domain, to choice 14, which is also in the negative domain, just with a probability that is divided by 4, right? So here we see a common ratio effect in the negative domain as well, and so compared to choice 11, we see a reversal of preference once we put a negative sign in front of the 4,000 and the 3,000. Right, so there's some interesting relationships once we move this common ratio effect choices into the negative domain. There's risk aversion in the positive domain and risk seeking in the negative loss domain, and that is observed exactly here, and that is able to explain all these choices. And of course, the choices in the negative domain, they violate expected utility with this common ratio effect, just like those choices in the positive domain. And the data is incompatible with a different model of risk preferences, which would be uncertainty aversion. So it's not that you prefer or are averse, so you prefer certainty, or you are averse to uncertainty, because it could go the other way around, as choice 5 shows, right? In choice 5, because we are in the loss domain, we are not just preferring things thanks to the fact that they would be with a probability of 1 and even yielding a lower loss. So it's not that we are always preferring things that occur with a probability 1. And that is shown in choice 5. So the data suggests that prospect theory, the way that it's modeled, with this very strong difference between gains and losses, is the way to explain this pattern. There's furthermore an isolation effect. If you look at choice 7, here there was a two-stage game. In the first stage, there's a probability of 0.75 to end the game without winning anything, and a probability of 0.25 to move into the second stage. If you reach the second stage, you have a choice between A and B, and we know from before that you would prefer B if you had these two choices. Your choice must be made before the game starts, that is, before the outcome of the first stage is known. And note that the final states of choice 7 are the ones of choice 11, where most people chose A. So if we go back to choice 11, we have it here, then you basically cut the probability by the factor 4 compared to choice 2. And so here we observe the same choice as in choice 2. So we understand that when you make the decision in choice 7, then you do not think about these probabilities actually being cut by the factor 4, as the description tells you they are, because there is this two-stage game, right? So this is the isolation effect. If you have this compound lottery or this sequential way of getting to this lottery, then you do not take into account that the probabilities are actually smaller. You do not take into account that this 3000 with probability 1 is actually not occurring with probability 1, because you only reach that stage with a probability of 0.25, right? So this violates the notion that the probabilities of the final states are decision relevant. So decision relevant seems to be here the probabilities in that substage of this game. So if you compare choices 7 and 11, then in choice 7 you first have this division as to whether you reach this point where you might get a payoff, or you with 0.75 probability you just don't get anything. And in choice 11 that's different, because there's first the decision that is basically made within the lottery, and then you have a split as to whether you get it or you get 0, right? So the reaction of the decision maker is different in these two sides, in these two choices. All right, and then we can have the isolation and the reflection effect at the same time. So choice 8 says, in addition to whatever you own, you have been given 1,000. You now ask to choose between lottery A, which yields 1,000 with a probability 0.5, or B, which yields 500 with certainty, and mostly people choose lottery B. And in choice 16, in addition to whatever you own, you have been given 2,000. You're now asked to choose between losing 1,000 with probability 0.5 and losing 500 with certainty. And you can see that in terms of final outcomes, these two choices are equivalent. But in choice 16, people would prefer to gamble about these losses rather than getting a sure loss, right? So this would be both the isolation and the reflection effect as we move from the positive gain domain to the negative domain in these sub-stages, even though the final wealth states described in choice 8 and choice 16, they are exactly the same. So there's risk aversion in positive prospects, risk seeking in negative prospects, and that's exactly what we see here, even though it's just a sub-stage of the lottery. Right, and I think this example has been used quite prominently in the work relating to prospect theory, where you can, there was an example, I think, about Chinese disease, where you could describe the outcomes of different medical options in two different ways, and then you could see that the decisions made by medical personnel would actually be differing, so they would choose different medical treatment depending on how you would frame the mortality of this disease and the mortalities of these treatments. So this looks very similar to these choices 8 and 16, what was done there in terms of a concrete application that shows that very important decisions might be subject to this effects. Okay, so my last slide on prospect theory shows you that small probabilities are usually overweighted. Here in choice 9, we have two lotteries that have the same expected value, but rather than getting a gain of 5 with certainty, people prefer to gamble, again going against this idea of uncertainty aversion, and try to get a payoff of 5,000. And if you move this choice into the loss domain, then you see a reversal of this. You would prefer to get the loss of 5 rather than gamble and might be maybe struck by a loss of 5,000. And that goes against the idea that you're risk averse in the gain domain and risk loving in the loss domain, but it can be explained by the fact that very low probabilities are overweighted, and then you would prefer to get the chance to get 5,000 in choice 9, but you wouldn't want to be confronted with a loss of 5,000 in choice 17. So you suddenly observe risk seeking in the positive domain and risk aversion in the negative domain. This brings us to the end of the section and the part of this lecture on prospect theory. The second part will be about mental accounting, and I hope to see you there. See you then.